In this video, we talk about static stress analyses, specifically their purpose, workflow, capabilities, and what results they produce. Perform a static stress analysis to determine stress, strain, displacement, and safety factor in a part or assembly resulting from various applied loads. You can also determine contact pressures between parts of an assembly. In order for this type of study to be valid, the model must have the following characteristics. For accurate results, stresses cannot exceed the yield strength of the materials. The loading must cause only small deflections or rotations, so deformation can't have a significant effect on the load direction, magnitude, or the surface area to which loads are applied. Also, the deformation can't alter where or in what manner the parts are constrained. Finally, dynamic effects from the loading are not significant. Static stress analyses do not consider damping or inertial effects, that is, momentum. This model is a three-part assembly consisting of a connecting rod and two round pins. A 2,000-pound tensile load is applied to the assembly. Separation contact is defined between the parts, meaning that the pins can freely slide along or separate from the connecting rod, but the parts can't penetrate through each other. Let's take a look at the process of setting up and solving the analysis. The first time you enter the simulation workspace, the new study dialog launches automatically. Choose the static stress analysis type. Click this icon to access the study settings. We'll define an absolute mesh size of 0.125 inch, which will produce two elements through the thickness in the thinnest regions of the connecting rod. If you want to make changes to the model for your simulation, use the Simplify command. The tools in the Simplify workspace enable you to remove unnecessary components or features, split faces to confine a load or constraint to only a portion of a larger face, or to provide edges or vertices for locating loads and constraints, or modify the geometry in any way you want to achieve the desired results. Any changes you make here affect only the simulation model. The production geometry represented in the model workspace remains unchanged. Click Finish Simplify to return to the simulation workspace. The materials were previously defined in the model workspace. We'll confirm that the study materials match the model materials. Let's apply the following constraints to make the model statically stable without impeding its expected displacement under load. Fully fix the ends of the small pin. You can left-click and hold the mouse button down to see a menu of items to select, including hidden ones. Apply a Z constraint to the straight edges on the large pin. This constraint prevents the pin from spinning in its hole and prevents the connecting rod from rotating about the center line of the small pin. Apply a Y constraint to the pin and connecting rod edges at the middle of the large hole. This constraint prevents the connecting rod from sliding axially along the small pin, and it prevents the large pin from sliding axially in the large hole. Next, apply a total load of 2,000 pounds in the -x direction to the ends of the large pin. Automatically detect all contact sets. The default tolerance is fine because the parts are touching at each contact face. Edit all contact sets to change the contact type from bonded to separation. Now let's clone this study to make a new one in which we'll use a different setup. In the Settings dialog, enable the Remove Rigid Body Modes option. The solver will stabilize the model automatically by adding a global acceleration load and soft spring constraints. Delete the fixed constraint on the small pin. There is now no X constraint anywhere on the model. Also, we'll balance the applied load with an opposite force at the ends of the small pin. This method will allow the small pin to rotate at its ends, behaving like a simply supported beam. In the first study, the pin behaves like a built-in beam due to the fixed constraint at the ends. The studies are ready to solve. When the solution finishes, the Study 2 safety factor results appear. The orange and white exclamation point indicates that the design is marginal. The result is greater than 1, meaning that the yield strength has not been reached. However, the safety factor is lower than typically recommended. Since we're going to look at the results of two different model setups, we'll go to the Compare workspace. Here we can see the two studies side by side. Ensure that Study 1 is on the left and Study 2 on the right. By default, the model viewpoint and result type are synchronized for the Compare windows. The minimum safety factor is greater for Study 1. We'll see why in a moment. Let's compare the von Mises stress results. In Study 1, the maximum stress occurs at the ends of the small pin, where it's constrained. In Study 2, the stress is greater and occurs at the middle of the pin's length, which explains the difference in the safety factors. Display the X displacement component. Notice that in Study 1, all X displacements are 0 or negative. In Study 2, because of the opposing forces, both negative and positive X displacements occur. The difference between the minimum and maximum displacement values is greater than the maximum displacement in Study 1. The reason is that the small pin bends more freely without the fixed constraints at the ends. Finally, the maximum contact pressure is greater in Study 2. The increased bending deformation of the small pin causes more localized contact between the pin and connecting rod, so this result is not surprising. Thank you for watching.